Today we're going to discuss the tools of the analysis the data. So I will start with the expectation, which is nothing else as the average. So let's assume we've got the random variable x, which is the number of phones sold in one of the local stores per day. Let's make the record of this x for the 6 days. So let's say x is for the first day there was only one phone was sold, 2 phones on the second day, 3 phones on the third day, 2 phones on the fourth, 1 and 5. So let's say now I would like to calculate how much phones were sold per day in the 6 days. So what I will do is I will just simply sum the 6 numbers and divide them to these 6. So basically the mean, or what I call this expectation of this random variable x, is the sum of all the values, all the outputs of this x divided to the n. So this will be 1 plus 2 plus 3 plus 2 plus 1 plus 5 over 6. So what I can do is I can write this down, all this data, in the table of the frequencies. So I will count how many times this x appeared, the 1 appeared. So 2 times, how many times the 2 appeared? 2 times 3 appeared once and 5 appeared once. So at the same time we can calculate the expectation by multiplying the output to its frequency and summing them and dividing them to the 6. So you can see that the both results are the same. So basically here, instead of just summing these 2 once, I just decided to multiply once to the 2. So at the same time we can calculate the expectation using the probabilities. We can get the probabilities using the frequency table by dividing each frequency to its to the total number of the frequencies. So basically the probability of getting 1 is 2 over 6, probability of getting 2 is 2 over 6, then 1 over 6, and 1 over 6. So basically this part of the table is called the probability distribution. Basically we've got this total probability which is equal to the 1 and distributed this over the all outputs of the random variable. And this table shows us how this 1 is distributed over the different values of this random variable. So using this, by dividing every 6 to every term to the 6, I can get the another formula of the expectation of the x, which is 1 multiplied to the 2 over 6 plus 2 multiplied to the 2 over 6 plus 3 multiplied to the 1 over 6 plus 5 multiplied to the 1 over 6, which can be written as the summation of every output multiplied to its probability. So basically xi multiplied to the p of xi and their sum, I from 1 to the n. So where n is the n different possible outputs of this random variable. I mean, you need to differentiate this n from this n. So here n is the number of the datas, and this n is the number of possible different outputs of the random variable. What I want is I would like to calculate some function, the expectation of the some function of the random variable. Let's consider the function g of x, which will be just simply x squared. So what I will do is, so once I've got the value of the random variable, I will square this, okay? So previously we've got a data, x was 1, 2, 3, 2, 1, 5. And every time when I will get the output for the random variable, I will just square this. So x squared will be 1, 4, 9, 4, 1, and 25. And what I want is, I would like to calculate again the expectation. So again, I can make the frequency table for the x squared by putting all the values of this x. So I've got 1, 4, 9, and 25. And I can calculate the probability. So I can count how many times I've got 1, 2 times, and divide this to the all possible outputs, so like all possible frequencies, so which is 6, total number of the frequencies. So I can calculate the probabilities by just dividing the frequency of every output to the total number of the frequencies. So here it will be 2 over 6, 2 over 6, 1 over 6, 1 over 6. So I can calculate the expectation of this random variable x squared is the summation of the x squared multiplied to the probability of xi. So do you see the difference between the formulas? So previously what we did is we calculated the expectation of the x by just summing the multiplications of the output to its probability. So here, when I take the function of the random variable x squared, I just have to multiply the value of this function to the same probability. Okay? So in terms of the different notation of the expectation, so the expectation of the x was previously the summation of the xi's over n. Now the expectation of the x squared is the summation of xi in the square over n. I can get this from here, right? So the average value of all these values is just their summation divided to the 6. We know the random variable with the probability mass function p of x. So what I want is, I would like to know, so what is the expectation? Is the expectation of the x is the summation of the xi multiplied to the p of xi. And what I want is, I would like to know what is the expectation of the function g of x, which is ax plus b, where a and b are t constants. So according to the formula which we've got previously, the expectation of the g of x will be the summation of the value of the g for every output of the random variable multiplied to the probability of this output of the random variable. And now I will substitute, instead of g of x, the ax plus b, and we'll get the following answers. So the summation I from 1 to the n, axi plus b multiplied to the p of xi. So since this is the summation, I can split the summation into the two parts. We can write it as a summation of I from 1 to the n, axi multiplied to the p of xi, plus the summation of the b multiplied to the p of xi. So since a and b are the constants, we can take them out from the summation and we can get the formula a multiplied to the xi multiplied to the p of xi plus b multiplied to the summation of all the probabilities. So obviously this is nothing else as the expectation of the x, and this summation is equal to the 1 according to the axioms of the mass function, or the properties of the mass function. So simply we will get the b. So basically we've got another formula. So the expectation of the linear function of the random variable is equal to the a multiplied to the expectation of the x plus b. So the conclusion from here is that the expectation of the constant is simply the constant. So the expectation of the constant is simply the constant. So we can explain this from this point of view. So let's assume your random variable y can take the constant value. So always it takes the b for all the experiments. So b is some value. And obviously when I find the average of all of these b's, I will need to sum this m b's, right? So a multiplied to the b, and divide them to the number of the b's, which is m. So obviously the average of this random variable will be b, or basically the average of the constant will be the same constant. So now let us consider the expectation of the following three random variables. So I've got the random variable x, which takes only the 0 with the probability 1. And I've got the second random variable y, which takes the -1 and 1 with the equal probabilities, which is equal to the 1 over 2. And I've got another one, omega, which is -100 and 100, so they're possible outputs, with equal probabilities. So basically taking the -100 or 100 are equal to the 1 over 2. So let us calculate the expectation of the x. So the expectation of the x is, according to the formula, output multiplied with its probability. So summation of the xi multiplied with the p of xi, which will be equal to the 0. Basically 1 multiplied to the 0. The expectation of the y is -1 multiplied to its probability plus 1 multiplied to its probability. It is also 0. The expectation of the omega is, again, -100 multiplied to its probability plus 100 multiplied to its probability. It will be also 0. So you see, so even though we've got these three different random variables with really different values, the expectation is the same. So basically, the expectation doesn't reveal us some properties of the random variables. It is really difficult to differentiate these random variables, to see some extra features of the random variables. So now, the idea would be to introduce another tool which we can use in order to make the analysis, or in order to differentiate the random variables. So this is what we call as variance. Variance. So variance is some measurement of how much the outputs of the random variables, or usually the data, is spread around the mean. Around the mean. So the idea would be to find the mean. So let's say I've got the outputs of the random variable x1, x2, x3, and so on, xn. So we know that the expectation of this random variable, so outputs of x, let's say x outputs, would be this summation of all the outputs, x1 plus x2 plus x3 plus and so on plus xn, and divide them to the n. So this gives us the expectation, or as we call it, the mean, basically, right? So which is constant. So let us calculate the mean, and now I would like to measure how these points are spread around the mean. The idea would be to find the distances from all the points, from the point, for every point, the distance between the point and the mean. So the distance between x1 and the mean would be x1 minus the mean in the square. The distance between xt and the mean would be xt minus the mean in the square, plus and so on, plus xn minus the mean in the square. So I'm taking the square because I want that the distance will be positive always. The reason why we're taking the square instead of the module is that this function is more nicer, so we can take the derivatives later on this function. So then now, as we say, the variance would be the average of those distances, right? So the variance would be the sum of all those distances, xi minus e of xi in the square, and divide them to the n. Okay, so we're here, e of x is simply the constant, so which we calculated before. So do you remember? So previously we said, okay, so the expectation of the x is the summation of the xi over n. The expectation of the x square is the summation of the xi in the square over n. So what is the summation of the xi minus mean in the square over n? So which is obviously so this is equal to the expectation of x minus the expectation of the x in the square. So this is how we would like to define the variance. Even though by the definition the variance is equal to this formula, it is really difficult to evaluate the variance just using this formula. The idea is to figure out some simplified version of this formula using the properties of the expectation. So what I will do is I will open up this bracket, so I will write, okay, so what is the expectation of the x minus e of x in the square? So this will be x squared minus tx multiplied to the e of x plus e of x in the square. So we know that since the expectation is nothing else as a sum, right? So we can take the expectation of every single term separately. So we can write as expectation of the x squared minus expectation of the tx, expectation of the x, plus the expectation of the x in the square. So please note that this expectation or this expectation in the square are just a constant. You can take them as you can denote them differently. For example, as the mu, and here is the mu square, or anything else. So basically, you can denote the mu as the expectation of the x. So here, the expectation of the x is just a constant. So we know that when we multiply the random variable x to the constants, we can take them out from the expectation, right? So we can write as the expectation of the x squared minus t expectation of the x. I just took out the constants, this t and the expectation of the x. And what is left is just simply x inside the brackets of the expectation. Plus the expectation of the constant is simply the constant, which we proved previously. So the expectation of the x in the square. So we've got t of the expectations of the in the square plus 1 expectation in the square, which will be minus 1 expectation in the square. So we've got a formula, the simplified one, which is the expectation of the x squared minus the expectation of the x in the square. So in order to use this formula, let us try to apply this to our previous example. So previously, we've got a data for the x. It was 1, 2, 3, 4, 2, 3, 5. Was the following properties, was the following probabilities. Previously, we've got the data 1, 2, 3. Previously, we've got the random variable with the possible values 1, 2, 3, 5, and with the probabilities 2 over 6, 2 over 6, 1 over 6, and 1 over 6. So the expectation of the x is 1 multiplied to the 2 over 6 plus 2 multiplied to the 2 over 6 plus 3 multiplied to the 1 over 6 plus 5 multiplied to the 1 over 6. So by calculating this, we get the answer t plus 4 plus 3 plus 5 over 6, which is equal to 14 over 6, or 7 over 3, right? So now in order to calculate the variance, so let's assume, let's say I would like to calculate the variance of this random variable as well. So I would like to calculate this using the formula e of x in the square minus e of x in the square. So in order to do this, we need to also evaluate the e of x square, right? So this will be equal to the 1 multiplied to the 2 over 6 plus 4 multiplied to the 2 over 6 plus 9 multiplied to the 1 over 6 plus 25 multiplied to the 1 over 6. Basically, the square of every output of the x multiplied to their probabilities, right? Then we have to add them. So if I add them, I will get the result 2 plus 8 plus 9 plus 25 over 6, which will be equal to 44 over 6, or if I divide them to the 2, it will be 22 over 3. Okay, so now the variance will be equal to the 22 over 3 minus 49 over 9, right? So by giving the common denominator, we can find that this is equal to the 66 minus 49 over 9, or simply 17 over 9. So this will be the variance of this random variable. This is just some measurement which tells us how far the points are spread around the mean. So the another example of finding the variance is more intuitive. So let's assume the random variable from our classical example. So x, let's say, is the output when we roll a die. So it can take the 6 different outputs. So it can take the 1, 2, 3, 4, 5, and 6 with the equal probabilities. The expectation of the x is the output multiplied to its probability in summation. So the expectation is when we multiply every output to its probability and then sum them. So we'll get 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6, which is equal to the 21 over 6, or 7 over 2. And now we will calculate the variance of the x using the formula, the expectation of the x square minus the expectation of the x in the square. So we've already calculated the expectation of the x, so now we need to calculate the expectation of the x square. So the expectation of the x square is the summation of the x square multiplied to the probabilities. So this will be 1 multiplied to the 1 over 6 plus 4 multiplied to the 1 over 6 plus 9 multiplied to the 1 over 6 plus 16, 1 over 6 plus 25, and so it is 6 multiplied to the 1 over 6. So if we sum everything, we'll get 91 over 6. So in order to calculate the variance, we just need to put the value. So this will be 91 over 6 minus 49 over 4. So I will give here the 2 and 3. So this will be 182 minus 147 divided to the 12, or 35 over 12. So the only thing which I would like to show at the end is to calculate the variance for the function of the random variable. Let's calculate the variance of ax plus b and try to get some rule to do this. In order to calculate this, let us write the variance of the ax plus b using the formula which we derived previously. So the expectation of the ax plus b in the square minus the expectation of the ax plus b and square. So we will take out the square, so we'll open up the bracket, so this will be a square x square plus t abx plus b square minus, so I will open up the brackets first, then we'll square this up. So the expectation of the x multiplied is a plus the expectation of the constant will be simply the constant in the square. So now I'm going to apply the expectation for each of the terms. So this will be the expectation of the x squared, where I can take out the constant out of the expectation, plus 2ab multiplied as expectation of the x, plus the expectation of the constant will be simply the constant, minus a expectation of the x in the square multiplied to the b square minus square minus 2ab the expectation of the x minus the b square. So we can cancel some of the terms, and what is left is this term and this term, so where we can take out the a square out of the brackets, and we can write this as the expectation of the x square minus the expectation of the x in the square, which is nothing else as the variance of the x. So that is why it will be a square multiplied as the variance of the x. So we've got a rule which tells us the variance of the linear function of the random variable will be a square multiplied as the variance of the x. So we can discuss why the variance of the constant actually is equal to the 0. So the variance of the constant is equal to the 0. So this is another rule which can be explained very intuitively. So let's assume I've got a random variable x which takes always the same value, which is b. So on the first trial it gave me b, then b, then b, then b, and so on. Right? So I've got m trials and m results which are the same. Previously we discussed that the mean or the expectation of this random variable, which is the average of all the outputs, it is like a b plus b plus b plus and so on, plus b divided to the m, gives me again the b, because there are m b's. So now if I would like to find the distances of from between each output and the mean, all the distances will be 0, 0, 0, 0, and so on. And the variance, which is the average of the distances, will be 0 because all the distances are 0.